Okay, hope everybody's doing well. Let's go over a couple of announcements and then we'll begin talking about inflation. Um, as a reminder, your big project assignment is due on Friday. And so hopefully you've made good progress on that. The main advice I can give you at this point is to please carefully read over the assignment instructions before you submit your report. The assignment instructions have been carefully designed and they've evolved over the semesters as I've noticed students forgetting certain things. I've put a lot of cautions and warnings and notes in there that you need to pay special attention to. And so that should be submitted before class on Friday, and if you have any final questions as you're working on that, feel free to get in touch with me and I'll do my best to address them. The next thing on your schedule after that project is a homework assignment that has to do with inflation. And we're going to begin talking about inflation today. So that homework number 12 is due on Monday of next week, and it's 9 problems long. And so it's one of the assignments where I make each problem a little bit simpler, but then there's more of them just so you get the repetition and the practice, and hopefully that will drive the concepts home and allow you to retain the information. So I'd encourage you to get an early start on that. Hopefully you're already done with the project and you've got plenty of time to work on the assignment. So are there any questions related to these announcements before we get into the inflation material? All right. Well, if not, then let's move forward. This is an image I found a while back advertising a car that I don't think they make Hudson's anymore. It's one of the great American brands that's drifted out of the public view. But back in 1950, you could buy a brand new car for $2,365. Now, cars these days are a lot more expensive than that, and especially if you consider what you were getting for that price. It's obviously a really enormous car, and it's got 3 adults in the front seat, and so it's got a big wide body, and it's really long as well. It probably weighs thousands of pounds of steel, and in contrast to the manufacturing methods that are used nowadays where automation and robots kind of enhance a single person's ability to get work done, cars back in those days were built almost entirely by hand. It was on an assembly line, but things were put into place by people. And so it was really expensive to build, but yet the price of $2,365 is a lot less than what we'd expect to pay today. And in fact, that it's not just this one particular car that was cheap. If you look back through advertisements of the time, you can find that even the used cars back then were quite a bit less. You'll see that there's some cars there for as little as $125, and maybe you could still find a car for $125 today, but it probably wouldn't start. It'd probably, maybe you wouldn't even be able to get the scrap for that. So things used to be less expensive than they are now. That's what we're talking about today, is the inflation effect. And in contrast to those inexpensive vehicles of the past, a new truck nowadays could easily set you back $70,000. And so here's a 2019 Ford F-150, one of the really expensive trucks that I don't understand why people buy, but plenty of people do. So $68,000. Why have prices gone up so much over the years? When you think about this is being made with the advantages of automation, it's being made with materials that are obtained more inexpensively. Mining is more efficient now than it was then, and many of the parts and materials are sourced internationally where labor costs are lower than they are in the United States. And so why does a car cost so much more today? Well, to answer that question, it's helpful to look back over historical inflation. And this is a figure from the Wall Street Journal that goes way back to the beginning of our country's history. If we go back to 1775 on the far horizontal axis, you can see that what this figure is illustrating is how prices changed on an annual basis. So the annual percent changes in the consumer price index. And so the consumer price index is kind of a weighted average of all the sorts of things that people would buy on a day-to-day basis. And so back in 1775, they weren't buying Ford F-150s, and they weren't even buying Hudsons for that matter, but what the consumer price index in those days would take into account is the food, the clothing items, the cost of housing, transportation costs, kind of a weighted basket of all the things that people would spend money on in those days. And so you notice that some years prices went up, some years prices went down. The shaded blue regions are indicating when prices went into what's called the deflationary period. And so over time there was quite a lot of fluctuation, sometimes going as high as 30% inflation per year. And think about how devastating that would be if next year things suddenly cost 25 or even 30% more than they cost now. Your savings wouldn't have quite the purchasing power that they had previously. And so if we zoom in on the more modern age, highlighted there in the yellow dashed line, we notice that the inflation has kind of calmed in recent years. Since the Great Depression, monetary policy and the Federal Reserve Bank has tried to keep inflation at a target rate of about 2% per year. And especially in recent decades, they've been pretty successful with that, managing inflation by managing the supply of money. And so that's really at the heart of what drives inflation is, number one, consumer sentiment, just the impression that people have of whether things are going to cost more in the future or whether they feel economically secure. And so that consumer sentiment drives demand, and we've already talked about the relationship between demand for goods and price. But then the other effect is the available money supply. The number of dollars that are in circulation directly affects how much prices are going to be. And here's a figure from the Wall Street Journal as well, which originates from the U.S. Labor Department. And this is showing how earnings have varied over the years. And so this is the average annual earnings growth. And so you see that maybe in some of the low years the wages are going up by just better than 1% per year. In a good year across the economy, maybe wages are growing 4% per year. During periods of recession, wages go down. But it's the money that people is earning. If people's income is going up, then the supply of money in circulation is higher, and then prices will be higher because it will be a greater number of dollars chasing a fixed number of goods. And so how many dollars it takes to purchase those goods will go up. The two main effects that I hope you keep in mind is, number one, that price inflation occurs when wage growth occurs. So if there's more demand for goods, then that's largely because people have more money. And then the other effect is that wages fall during periods of recession. And I think it's pretty well accepted that right now, at this present moment in time, when a large part of the economy has been halted because of the coronavirus, that we have more unemployment than we've ever had before as a country. And it's likely that because of the wages falling, that there could be less demand for goods, and so we may see less inflation than there's been before. So let's go through some of the terminology here before we do some calculations. What we mean specifically by inflation is how much money is needed to obtain the same goods or services. If we express that as a rate, like as a percentage on an annual basis, then we call that inflation rate and assign it the variable f. In the calculations we'll do today, we've got a couple of formulas, and f is a rate, a percentage on an annual basis where we're looking at how much prices are changing. Now, an important note, the subpoint that's listed there, is that if your savings account only earns as much as the inflation rate, then it effectively means that you're actually not gaining any purchasing power. So think about this following scenario. What if prices year over year are going up 2% per year, and I put some money into the bank? Well, that means that in the future I'll be able to buy the same amount of things that I can buy now. And so really, I haven't had any net benefit for deferring the satisfaction of spending my money. I have no gain in the purchasing power. And in fact, if your savings account rate is less than the inflation rate, then in fact you're being penalized for saving money. And that's been the case for about the last decade, that the savings rates that are offered by banks is less than inflation by a little bit, so that your purchasing power has been eroded due to inflation. So if we want to ensure that we have a gain in purchasing power, then we would make sure that the real interest rate, I, is positive. And so we're going to distinguish between a market interest rate, which I'll show you the formula for on the next slide, and then the real the real interest rate. So the real interest rate would be an interest rate that means you can buy more things in the future because you've saved. So the inflation-adjusted interest rate, also known as the market interest rate, is what banks actually pay. If you go online and look at Chase Bank or Huntington Bank or any of the banks, when they actually advertise an interest rate, what they are advertising is their market interest rate. Sometimes in theory or textbooks it's called the inflation-adjusted interest rate. And here is the formula for how we would determine inflation-adjusted interest rate as a function of the real interest rate and the inflation rate. So remember that the inflation rate is assigned the variable f, and the real interest rate is assigned the variable I. And so if we want to know the present value or the present cost of some item where we know the amount in the future, and we're taking into account both the inflation and some real rate of return, then we have to multiply those two together. And so the formula for it, where we're accounting for the inflation and for the interest, is that the market interest rate is the real interest rate plus the inflation rate plus the product of the two. So we'll use this formula in our in-class exercise today, and then several of your homework problems also use this formula. So you should look for I to be positive if you want to have an increase in purchasing power. Now, on the subject of purchasing power, let's just look at the following illustration. Let's say that there's a basket of groceries, and it doesn't necessarily need to be just all produce like is shown there, but it could just be some things that you go buy today for $25. And if we assume that prices are going up by 3% per year, what would the price of that basket of goods be after 15 years? So you've seen the formulas before. Remember the equation method where F equals P times 1 plus I to the n power? I'm sure that formula is probably burned into your memory at this point in the semester. Well, I in that formula means interest rate, but we can use it also, the form of that equation, for inflation rate. So here you can see I've substituted in the letter F into that formula that we've seen plenty of times so far this semester. And so if we want to know what will the price be in the future, then that future price will be the current price multiplied by 1 plus the inflation rate to the power of n. So if you substitute in 1.03 to the power of 15, then that gives you the factor. and multiplying the factor by $25 tells us that we'd expect the price in 15 years to be $38.95. So that's how you can find the price of the basket of goods. But what is your purchasing power? So continuing this illustration, let's say that you saved $25. Instead of buying the basket of goods, what if you saved that same number of dollars and you put it into a bank account and the bank is paying 7% per year? So what this question is asking is, how many baskets of food could you purchase? So two things are happening. You're going to have more dollars in the future than you have now because you're investing it. But at the same time, the price of the item will have gone up. Because in 15 years, you're not going to be buying that basket for $25. You're going to have to pay $38.95. So first things first, we have to find out how many dollars will you have after 15 years. So it's going to be the same form of the equation. We'll use this form to solve for the number of future dollars you have. So it'll be 25 multiplied by 1.07 to the power of 15. So if you do that, $25 compounded 15 years in the future will mean that you have $68.98. So how many baskets of food can you buy? Well, you're having to pay the elevated $38.95 price, so that means you'll be able to purchase 1.77 baskets of food. So that's an illustration of how your purchasing power went up over time because I was greater than F. Today we could only buy one basket of food, but if we defer the purchase for 15 years, we could buy 1.77 baskets because 7% is greater than 3%. So the difference between the two represents our increase in purchasing power. Any questions so far on these concepts? Okay, I sent out an in-class exercise paper maybe about a half hour ago, and in that activity we are going to look at an item that costs $5,000 now, and we expect it to experience 4% per year price inflation during the next several years. And so we want to know what's the cost in 5 years, what inflation adjusted interest rate should be earned, and then how much should we invest today. Now the paper that I sent you is slightly modified from that. I made it a little bit easier. Let me open up that in-class exercise paper and bring it up on the screen just to show you what I mean. Okay, I've defined the variables to make it a little bit simpler for you, just to drive the point home. I've identified what is F, what is I, what is I sub F. So what I'm going to do is I'm going to pause for a moment and give you some time to run the numbers on this, to try and calculate in part A, how much do you expect this item to cost after 5 years? It's $5,000 now, so how much will it cost for part A? Part B, you find out how much the I sub F should be if you want a real interest rate of 10%. And then finally, how much money should be invested to purchase the item in 5 years. And that's going to be using the same formula that was just on this illustration. For part C, you're going to be using this formula. Alright, so let me pause for a moment. Feel free to ask questions or chat in the text box if you have any questions about it, but I'd like you to, this will mean more. You'll be better off for the homework if we go through this in-class exercise with you crunching the numbers rather than just me showing you the solution right off the bat. Alright, so This question, part A, is asking how much is the item going to cost. So it's 5,000 now, so P is 5,000. And we're going to multiply it by 1 plus the inflation rate to the n power. So 1.04 to the 5th power gives a factor of 1.21665. And if we multiply that by the 5,000, then you should get that the cost of the item after 5 years would be $6,083.26. So that is how the price will inflate. Now part B says you want your investments to earn a real interest rate of 10%. If we go back here to the terminology, the real interest rate is I, and so we're saying that in this formula, I, we want to be %. And so what is I sub f, the inflation adjusted interest rate? And so the real interest rate is 10%, the inflation rate is 4%, and that means that we want our account to earn 14.4%. And so if your bank is actually paying 14.4%, then what that means is that once inflation takes its toll, then you will have each year increased your purchasing power by 10%. So in part C, how much should be invested today to purchase the item in 5 years? So if we know that the future cost is $6,083.26, and the account that we're investing in pays 14.4%, then we're trying to figure out how much to actually put in the bank. So just to summarize in the symbolic terms, you can see that P is the unknown that we're solving for after 5 years. And so now we use I sub f in the formula, the same kind of formula where we're relating future and present together. You know, what variable we use inside those parentheses. It can be I if we're solving with real interest rate. It can be f if the problem is asking us to take into account inflation rate. But here we're going to use the market adjusted inflation rate. And so if you invest $3,104 today, then that means you'll have $6,083 in your account after 5 years. And then that's how much you would need to be able to purchase that item that costs $5,000 today. So you can either pay $5,000 today and keep it in a warehouse, or you can put $3,104 in the bank, not have to warehouse the item, and you'd have enough money to purchase the item after 5 years. Any questions about this part 1 of the in-class exercise before we move on? All right. Well, the second part of the in-class exercise is looking at a really large aircraft that I first flew on about a year ago. I flew on an Airbus A380. It's an enormous double-decker airplane, and the cost of it when it was new was $340 million for a single plane. And let's just use that as a hypothetical, and let's say if we assumed that the price was going to be going up by 9% per year, then how long would it take until the cost is $500 million? And there's several ways you could do that. One approach would maybe be with Excel. And so let's just consider how we would set up a problem like this in Excel to find out how the price of an item is increasing over time. If we had some interest rate, I guess we'll call that F to represent the inflation rate. And in this illustration, we are assuming that the 9% per year, and it's originally $340 million. So 0.09, and we'll have the year and then the amount. So in year 0, the price of the item is $340 million. So 340 million. And in year 1, then it's going to be 1 plus I, which in this case is the inflation rate, times the previous year amount. So after 1 year, that same airplane that originally cost $340 million is now going to cost $370 million. And so we could continue this trend onward and see how many years is it going to be until the price crosses the $500 million threshold. So according to this Excel approach, it looks like the price would go from $480 million in year 4 to $523 million in year 5. But you don't always have Excel. So the hint that I gave you on the in-class exercise paper, if we scroll down to the thing that I emailed you before class, is I gave you the hint that you can use the log function on your calculator to solve this problem. So what we're solving for is the time. And so if you look at the relationship between future is equal to present 1 plus f to the n power. So what we're solving for is, this is the equation. Future is 500 million, present is 340 million, f is 0.09, and we're solving for n. So we want to know how many years is it. And so if you rearrange that algebraically, then you can solve for the number of years with your calculator and not necessarily relying on Excel. So let me give you a moment to try and jot this one down on paper, crunch the numbers, and then we'll revisit the solution together. Alright, so what do I mean that you could use the log function? Well, here we go. Alright, so we know that the price of the item is inflating by 9% every year, and the present value and the future value is given in the problem statement. And so what we're trying to solve for is n. n is in the exponent. So if we rearrange this equation, we can get n out of the exponent by taking the log of both sides. And so if you rearrange it algebraically so that p is in the denominator of the left side, and you take the log of that function, and then taking the log of this allows you to bring the n out of the exponent down in front of the log. That's just hopefully something that you remember from algebra, the log properties and exponential properties. So then we rearrange to solve for n, and you can see that that should cross over to the $500 million price after 4.475 years. So if this was assuming continuous compounding, or if we were doing the price adjustments on a continuous basis rather than in individual discrete year increments, then it would be after 4.475 years. Okay, so since we have a little bit of extra time, I just want to bring up on screen the homework assignment just so that you get your eyes on that. There are several problems here that's just kind of basic finance type problems that are using inflation concepts where you're going to be using the formula that I've introduced today, the formula that relates market interest rate with real interest rate, inflation rate, and the product of the two. So this equation is used in many of the problems on your homework assignment. But then I'm also asking you to solve for amounts and how much would you need to put into the bank now to be able to buy some item in the future, those type problems. So remember that assignment is due on Monday, and if we just take a look at these announcements, the big thing that you have on your to-do list is the project is due on Friday before class. So we're down to about 47 hours to do that. If you have any questions, please feel free to send me an email, or I can stick around here in the Blackboard Collaborate classroom for a few minutes if anybody has questions, but that's all I have for you today as far as the new material goes and the lecture. We are done, so I will see you on Friday. Take care, everyone.